Hi everyone, welcome to this video entitled System Discretization. This is the outline of this video. We will see an introduction. We will show how to do the discretization of a low-pass filter as a first example. Then we will show how to do the discretization of the small signal model of the current mode buck DC-DC converter that we have seen in previous video. And we will be using Qspice simulations to verify the correctness of our discretized systems. Here we have some relevant videos that might be of interest to you. We have Qspice number 2, digital PWM and signal sampling. Qspice number 3, closed loop, digital control of a buck DC-DC converter. Qspice number 4, frequency response analysis of DC-DC converters. Power electronics number 65, effect of sampling period on the closed loop response of DC-DC converters. And finally, power electronics number 66, digital control of a current mode DC-DC buck converter. Today we are going to be using many of the ideas that we have employed in these previous videos. So if you are not familiar with some points in this presentation, please take a look at these videos. This is the schematic of a digitally controlled DC-DC converter. We have the digital compensator, the zero-order Hall block, the plant, the sensor to measure the output voltage, and then the sampler to generate the sampled output signal to be compared with the reference. We have seen this in this previous video, Power Electronics 65 and 66. And what we have done in these previous videos was to design everything as an analog system in the Laplace domain. And then we get an analog compensator that we transform into a digital compensator using the Qspice approximation, for example. But as we have seen in these previous videos, there is another possibility. We can discretize the analog part of our system, in this case the plant corresponding to the control to output transfer function and the analog sensor, and then do the complete design of the discrete system in the Z variable domain. In this case, the response of our system in closed loop is as shown here. On the denominator, we have the product of the transfer function in the Z domain of the compensator times the transfer function of the product of the zero-order Hall block and the plant. We are calling this BGC of Z, and on the denominator we have this expression, so it's 1 plus the digital compensator, the transfer function of the digital compensator, times the discretized version of the blocks corresponding to the zero-order Hall block, times the plant, times the sensor. So today what we are going to see is how to discretize systems so we can obtain these transfer functions, and we will verify everything using Qspice simulations. So here we have the block diagram of the discretization of a system. In this case is the system f of s is the transfer function of our system. We have a discrete input variable here. We have the different values of the input variable. So we use a zero-order Hall block to generate an analog variable that is going to be at the input of our system, and then the system will generate the analog output. If we use a sampler here, then we can get the discrete output variable. Usually we don't do this because we are interested only in having our analog signal at the output, and this is why we are drawing here the sampler with a discontinuous line. But from the mathematical point of view, we are interested in getting a transfer function in the Z domain that is going to be like this. We have the Z transform of the discrete output variable and the Z transform of the discrete input variable. So we are interested in getting this transfer function that we are calling bf of z. And note that this is not the same as b of z times f of z. This is the complete transfer function of the whole system that we have here. So now, in order to obtain this transfer function in the z variable domain, we start with the analog domain. So the transfer function of the two blocks is b of s times f of s. And we know that the zero-order whole block has this response. So it's this times f of s, and we can express it like this. So if we take the z transform of this and of this expression, we get this expression here, and from it finally we get this final equation that is the one that we need to obtain the z transfer function of our complete system. So is 1 minus z to the minus 1 times the transfer function of our analog system f of s divided by s. To understand this process better, let's start with a very simple system. In this case, we are going to discretize a low-pass filter, so we are going to create a digital low-pass filter. The analog version of the filter is like this. We have the resistor, the capacitor, and the transfer function in the Laplace variable domain is like this, where omega sub 0 is 1 over r times c. So now, as we have seen in the previous slide, we have that the transfer function bf of c is obtained as the z transform of b of s times f of s. So we have obtained previously this expression. So we can get to this other equation in which we need to calculate the z transform of this expression here. For this, if we go to a table of the z transforms, we can get this equivalence. So immediately we can get that the transfer function bf of z is this expression, and if we operate a little bit on it, then finally we can get this equation here, which is the discrete difference equation that we can implement in our microcontroller or DSP in order to implement a digital low-pass filter. So now let's do a couple of simulations to verify that this is correct. So here we have the first simulation. We are generating the output of the filter in three ways. First, we have here the output of the analog low-pass filter. So we are injecting the sinusoidal voltage directly to the analog filter. Here with the C++ module, we are going to generate at this out here the sampled input voltage, and then using the analog filter to obtain the filtering version of the sampled input voltage for comparison. And finally, at this output here, we are generating the output of the complete digital low-pass filter. We're going to do several simulations at different frequencies, and then we will be plotting all the waveforms. And with these three statements, we are measuring the frequency response of the three circuits at each frequency. So we can take also a look at the content of the C++ source. Here we have the definitions, we have the current sample of the input voltage, the previous sample of the input voltage, the current sample of the output voltage, and the previous sample of the output voltage. And here, using the technique that we have seen in previous videos, we are saving the values of the previous samples. We are measuring the current sample of the input voltage and then generating the current sample of the output voltage using the expression that we have just seen. And here we are sending the samples to the outputs of the module. So with this we can run the simulation now, and here we have the results for the first frequency, which is 50 Hz. So on this window here, we are showing the analog input voltage, the analog output voltage, and the sampled input voltage. So we can see that all of them are almost the same. We are at a very low frequency, 50 Hz, and our sampling period is 10 microseconds. And here at the bottom, we are showing the output of the digital filter, the output of the analog filter with the sampled input voltage and also the input voltage. So we can see that all of them are almost the same, but if we do a small zoom, then we will see that we have the sampling in the output of the digital filter. So let's try other frequencies. For example, if we increase here the frequency to 100 Hz and run the simulation again, then we can see that the output of the analog filter is a little bit lagging the input voltage. So here also both of them, the output of the digital filter and the output of the analog filter with the sampled input are also pretty much the same, and they are very similar to the output of the analog filter. So let's try, for example, 1 kHz now, and then run again the simulation. So now we can see that again this in green is the output of the analog filter. We can see the input of the analog filter and the sampled input voltage, and here we have the signals, the output of the digital filter and the output of the analog filter with the sampled input voltage. Again, they are very similar and pretty much the same as the output of the analog filter. If we move this here below, then we can see that they match each other very well. So we can take this again up and then try, for example, 10 kHz and run again. So now we can see that because the sampling period is 10 microseconds, we have a much higher distortion on the input voltage, on the sampled input voltage, and this here in blue is the output of the analog low-pass filter, but with the input corresponding to the sampled input voltage, and in red we have the output of the digital filter. So we can see again that they are pretty much the same, but we start having some phase lag between them. If we remove here the input voltage to see everything better, we can see the difference. If we move this one to the top, then we can see that the output of the digital filter at the instance of the sampling is exactly the same as the output of the analog filter with the sampled input. So of course, now if we want to have more accuracy, then we should here decrease the sampling period, run again the simulation, and then we will have a much better response of our digital filter. Here on this part we can see the values corresponding to the gain of the three outputs and the phase, the magnitude and the phase. So we can see that the magnitude is pretty much the same, the phase is a little bit different. This is the phase of the analog filter, this is the phase of the analog filter with the sampled input. So we can see that there is a small phase lag compared with the analog output, and then we have even a higher phase lag at the output of the digital filter. Even we can try here 10 microseconds and run again. So we can see that now the difference is even much greater. So now we are going to do a simulation to plot the magnitude and the phase in Qspice of the three outputs as a function of the input frequency. This is the circuit to do the frequency response analysis. So in this case, what we are doing is changing the frequency at the input, and then with these statements corresponding to the frequency response analysis, we can obtain the magnitude and the phase at the three different outputs. We are doing a simulation from 100 Hz to 100 kHz, 10 points per decade. We are giving 20 periods to get steady state, and then 2 additional periods in which we are going to save the data to do the frequency response analysis. And all these statements here are used to do all the different calculations and the plots in different graphs. If you are not familiar with frequency response analysis in Qspice, please take a look at this video, Qspice number 4, in which you can find more information about this type of analysis. And here we have the plots that we obtain for two different sampling periods. For 1 microsecond, we can see here the different magnitudes, so we can see that from 100 Hz to 100 kHz they are exactly the same, but in the case of the phases we have some differences. They are pretty much the same up to 10 kHz, but beyond 10 kHz in green we have the response of the analog filter, so here we have minus 90 degrees phase lag. But in the case of the analog filter with the sampled input, the phase lag is greater, and when we implement the filter digitally, we can see that the phase lag at high frequencies is even higher. In the case of 10 microseconds sampling period, we can see pretty much the same effect, but now because the sampling frequency is 100 kHz, when we go close to 50 kHz, then we start to have some strange response because of the effect of the sampling. We can understand a little bit better the behavior of the phase in the different circuits by doing this AC simulation in Qspice, in which we are comparing the response of the analog low-pass filter with the response of the analog low-pass filter after the sampler. Note that in total we have three different situations. We have, of course, the analog filter. We have the analog filter with the discrete input variable, as we have seen in previous slides. So here we have the sampled input, in our case of the input voltage, and then we are using the zero order whole block and then the response of the filter, and we can model all this using this expression here. And then of course we have the response of the discrete implementation of the digital filter, which is given by this block here, and the final expression is obtained with this equation that we have seen, and so on. So with this circuit we are plotting the analog low-pass filter and the analog low-pass filter with the sampled input. There is a small detail here. Note that in the Laplace expression we are including in the denominator the sampling period, and this is so because here we want to include the gain of the sampler in the expression, but we are not doing this when we are doing the discretization. Here we don't have at the denominator the factor corresponding to the sampling period, t in this case, because what we want to model is only this part corresponding to the zero order whole block and the analog system. And this is so because we want to obtain this function which has a discrete variable at the input and a discrete variable at the output. So with this we can run the simulation and see the results. So here we have the results. This is the circuit, and here we can see in green the phase corresponding to the analog filter, and in blue the phase corresponding to the analog filter but with the sampled input. And if we compare this with the response that we have obtained before, we can see that it's pretty much the same, but of course we can only see the response of the digital filter by doing the simulation using Qspice and the C++ module that we have seen before. Here we have a more detailed comparison of the frequency responses. Here, using the frequency response analysis that we have just seen, the magnitudes are the same and the phases in the case of the analog filter with the sampled input and the digital filter. And here on the right is the .ac analysis of the analog filter in green and the analog filter with the sampled input. So we can see that this response is the same as this one here. And of course, the response of the digital filter can only be obtained by frequency response analysis and using the Qspice simulation with the C++ module. Well, this presentation is getting long. We have seen the introduction and the discretization of a low-pass filter. So in the next video, we will see how to discretize the small signal model of the current mode buck DC-DC converter. So we can use this model in future videos also. Thank you very much for watching this video. Please let me know if you have any comment or question, and I hope to see you in the next video. Goodbye now.